Greetings and welcome to Technology and Organisation 2020 Lecture 11, all about the singularity and related technologies. I'm Chris Barnett and I'm delivering this lecture via video because of course of the coronavirus pandemic, and I do hope in that context that you're all keeping as well as you can in this very unusual world we're in today. So let's turn to the reading for this lecture, which we have here on this slide, and it's basically separated into three. Initially the next big thing chapters, which give you a general overview. We then got various references on particular topics as we got down there. I would note that the Majlish book is the oldest reference on the module, the fourth discontinuity, massive conceptual book. You're unlikely to go and read the book, I'm sure, but you'll find bits about that in the next big thing chapters. And then finally here we've got a couple of references taking you out to some of the wackier places on the internet where you'll learn about the singularity and related technologies. The other set of references here are they are compulsory, because what I'm going to do here is not go through everything in detail in this particular video, but refer you out to these videos I've already produced, as it says there. So I thought rather than duplicating content I've made for public consumption already, where we talk about quantum computing. I've got a video I made last year all about quantum computing and applications, and where we talk about things like brain interfaces and cyborg fusion, I've got videos on those as well. So what I hope you do is to watch this particular video and also watch those three videos to get the full picture on this topic. Now, many years ago, back in the 1960s, 1961 to be accurate, a science fiction author of the time, Arthur C. Clarke, and a very well-known scientist, the guy who invented the communication satellite, he had this fantastic quote. He said that any sufficiently advanced technology is indistinguishable from magic. And really the whole idea of the singularity is bound up in this idea that things that seem impossible but which can be achieved technologically are linked to a point in time beyond which we cannot see. And this is really what this whole topic is about, a point in history, sometime ahead, is it in the 2030s perhaps, where the impossible, things that seem impossible to us today, become possible because of technological progress. And as it says on the screen here at the end of this second bullet point, again, this has happened before. If you imagine trying to describe your life today to someone from 50 years ago, or let alone 100 years ago, you wouldn't even have common points of reference to explain how you spend your time. On the internet, what's that? It's this thing on your computer, what's that? How's that run? Well, it's connected to electricity, what's that almost? Things have changed so much in terms of human activity because of technology. And this is a recurring theme. So the singularity is associated with the idea of a black hole. Yes, it is. A black hole in space sucks in everything, including light. You can't see beyond the edge, the rim, or the singularity of a black hole, which is a point beyond which we cannot see. And that's what the singularity is about, this point beyond which we can't see, we can't guess where technology will take us. But it's based on the idea of exponential technological progress. Every bit of technological progress we make builds on the technology before, particularly in the area of digital technology, and it might lead us to a point where things that would to us now seem to be magical are perfectly possible. The same way that the smartphone you have in your hand does extraordinary things that would seem magical to people not that many decades ago. Now, the singularity is often associated with artificial intelligence, but it involves a lot more than that. But let's start out with AI, and this is what's called the singularity loop, which gives us the basic principle. The idea that intelligence creates technology. People can create computers, for example, and then that technology allows us to make things which are more intelligent. Computers help us to make more sophisticated computers. That's been going on for decades, and we go round and round in a loop. So sometimes people say the singularity is all about us creating machines that are more intelligent than ourselves, sentient artificial intelligences, artificial general intelligences, as some people describe them, and that's what the singularity is about. And I think that's a deeply naive view of the singularity concept. It is associated often with the creation of beyond human intelligence, because it's beyond human intelligence which allows us to do things that we currently think to be magical with technology. But you can create beyond human intelligence without having a sort of entity by itself which is more intelligent than us. You could do it, for example, by linking people together to share their intelligence, which is clearly happening now using computer-mediated communication, using the internet. You could do it by taking people and augmenting their intelligence, either by augmenting them biologically, by linking them into computer technology, cybernetically, that type of thing. So don't get caught in this idea that the singularity is all about the creation of robots and artificial intelligences more intelligent than us that will take over the world. That, I think, is not really what this concept is really about. It's about saying we will have forms of intelligence, probably involving linking people to people and people to technology, which enable us to achieve things we can't currently achieve. I thought we should just put up again this slide you've seen several times in the module. You saw it in the first lecture, sometime since. It's now the last formal lecture, so I thought we'd put it up again. And I won't go through everything on here, all these different forms of technology that could engender radical change, digital transformation. But a lot of these are associated with the singularity. Obviously, artificial intelligence is associated, I've just been talking about, robots potentially as well. But for example, synthetic biology. One of the things that's going to become possible, which seems impossible today, is that we'll be able to digitally manipulate organic matter. We're just starting to learn to do this, as you learned in the synthetic biology lecture. It's been the case until this point in time that digital technology has been inorganic. We've not been able to change the world around us very much, a bit of genetic engineering maybe, but not really complicated control. We've not been able to re-engineer our own bodies in an organic sense, but that's starting to become possible because of the combination of synthetic biology and artificial intelligence. Again, you see exponential progress. Developments in computing, cloud computing, big data, AI make synthetic biology possible, drives the thing forward. And if you look across the bottom of this slide here, you see things like molecular self-assembly, learning to put things together inorganically in an organic kind of manner, if you like. Quantum computing we'll come on to in a second. Organic computing, cybernetic interfaces, again about linking people to technology or potentially making organic computing devices, which of course our brains are already, but making them in other ways, linking them together. This is maybe where the singularity is taking us. Let's look at a few particular areas that singularity is associated with. The first one is computing itself, and back in 1975 the guy who was chairing Intel at the time was George Moore, and he predicted at the time that computer technology would double in power and halve in cost roughly every sort of 18 to 24 months, and he'd made this prediction again more formally in 1980. And that has continued to be the case, but we will eventually reach a point where the power of the microprocessor can't be improved on at that rate. We can't shrink things down in terms of the components inside the chip endlessly. Eventually we'll hit atomic limits. And that's got people thinking about what is the next development in computing beyond silicon microprocessors. And there are people, for example, working on DNA computing. University of Manchester's got people working on this. If you want to know about this, I've got a video on organic computing, which we'll link for you if you want to watch on that. It's very experimental at the moment, but it looks like it could be possible. We could use DNA to make very sophisticated organic computers. We've also got people working, and many companies working, on quantum computing, which is far more advanced, far closer to being applied in a practical way. And quantum computers differ from conventional computers because they process data not using bits, which can be ones and zeros, ons and offs, but using qubits, quantum bits. And the thing that's weird about a quantum bit, which it can be 1 or 0 or both of those values at the same time, because a qubit can assume a superposition. That's a very weird idea, something that can be two things at the same time. Qubits are represented, for example, by the spin direction of an electron, the polarization of a photon, of a subatomic particle. So we'll just have to accept for now that this did happen. It's very, very weird. The application of quantum computing, though, I think is fairly easy to get your head around. One of the things that we're likely to use quantum computers for is molecular modelling, building models, building representations of the physical world. And the reason this is so significant is at the moment we can't model molecules really accurately using conventional digital computers, because molecular systems, all the organic matter in the world, you, me, drugs, everything else, we're all actually quantum in nature. And you can't model a quantum system unless you've got a quantum system to do it. And that's why quantum computing is so significant. So one of the big messages to take about the development of quantum computers is they will enable us to model the physical world in a way we can't at the moment. And that will enable us, for example, to change our understanding and our practice of things like physics, chemistry, biology, engineering, healthcare, things like that, which is of course extraordinarily significant in terms of its actual implication. As it also says here, we're going to see quantum computers used for things like optimizing logistics. There are already experiments going on in looking at traffic flows in cities using earlier quantum computers, and potentially quantum computers will be used to help us build more sophisticated neural networks and AI systems. It's also worth pointing out this is not just theory. We've already got working quantum computers, at least experimentally. A company called D-Wave Systems in Canada sold the first, what it called, commercial quantum computer to Lockheed Martin back in 2007, and IBM launched something called the IBM Q System 1, another experimental quantum computer, in 2019. It's also the case that the past few years now, both IBM and Alibaba in China have had experimental quantum computers available to access over the internet. You can already have cloud-based quantum computing. And there are various other pioneers. Google's doing a lot, Microsoft, Intel, various startups, as you can see on the slide here. And if you want to know more about quantum computing, as I said at the start of this video, do watch the quantum computing update video. Moving on, let's think about the singularity in the context of cybernetics and cyborgs. Back in 1960, two researchers working on space travel, Kleins and Klein, I always find it amazing they had very similar names spelled slightly differently, they were thinking about what it meant, what it would mean when human beings left the Earth. And they were thinking that basically our bodies weren't really adapted to working outside of the atmosphere, out in zero gravity, out in space. And so they assumed we'd have to change our bodies. The same way that when our ancestors left the oceans, we had to develop lungs and have new bodies at that point. They thought the same thing would happen again. And this would happen artificially. We'd be fitted with cybernetic parts, artificial parts, which would turn us into cyborgs. So that's where the idea of a cyborg came from. It came from real scientists thinking about humans changing themselves many years ago. Now, today, lots of people have artificial parts. The average person in a developed nation, when they die, has got a 50% chance of having artificial parts in their body, whether they're teeth, heart valves, hernia meshes, whatever they are. So the idea of putting inorganic stuff inside ourselves to keep ourselves living and to improve our quality of life has been going on for years. But what is changing is this technology is getting smarter. Most obviously, we've now got about 200,000 people alive today who've got a cochlear implant. So they've got a direct link into their auditory nerve so they can hear using electronic technology. We've also got a company called Second Sight who are developing retinal implants, where you could actually have a chip called the Argos 2 implanted on your retina, which stimulates the retina and gives sight back to certain people with various visual problems. And they've even now developed something called the Orion 1, which gives you a direct input to the optic nerve, so you can bypass the eye entirely for people who are blind. This is still very, very early technology, but the point I'm making here, we're developing interfaces to allow us to send electronic signals directly into a human being, which is an extraordinary concept. We're also starting to see the ability of human beings to control their body using electronic systems. This is just coming in to help disabled people. For example, there's a lot of work going on, not least from the US military and related research organisations, using what's called myoelectrics, which is where you actually read signals from the muscles on the skin, and what's called targeted muscle renervation. So, for example, if you've got someone who can't move their arm because they've got damage to the nerves in the top of their arm and their shoulder, you can take signals from the nerves in at the top of their chest and route them down, lower down the arm electronically to control the hand, which is a really extraordinary thing. It's starting to be done, again, very experimental, but it obviously helps people with particular conditions. Sort of linked to that, we're also learning how to develop more general brain-computer interfaces, BCIs. So we can literally link people directly to computer technology using electronic systems. This can be done non-invasively using something like an EEG headset to read brainwaves, and you can then take brainwaves and actually induce them back into somebody's head using a massive TMS coil, basically a massive electromagnetic system you put on somebody's head. And there have been experiments done at University of Washington where people have been linked together over the internet, one wearing a headset, an EEG headset, one wearing a TMS coil, and ideas or at least sensations have been transferred from one person's head to the other, so they could, for example, play a computer game, coordinate their actions using brain interfaces. We've also got the development of invasive brain interfaces, where you literally have a chip put in your head. There is a particular chip called the brain gate, which is a 4mm square little array of electrodes, 100 electrodes you can implant into the brain surgically. You wire it then up out to a computer device that interprets those signals. This has been implanted into a monkey who's learned to control a robotic arm to feed itself. It's been put into several people who've also learned to control robotic arms. So we're at the very start of work in linking ourselves directly to technology. And if you want to know more about this and how this could become the next human-computer interface potentially, you can look at my videos, first of all on brain-computer interfaces, which takes you through some of these extraordinary experiments. I even try a brain interface out myself, not a surgical one, but I try one out in this video. And there's a video on cyborg fusion that thinks about the broader implications, not least for businesses, of what happens when this technology comes into a more widespread use. Moving not that far away from this, let's think a little bit about genetic medicine. The idea of coming back to the fact we're entering a period of time where we've got more and more understanding and control of organic matter, including the organic matter of our cells. Between 1990 and 2003, we had the Human Genome Project to map the human genome, all of the code in our DNA. And when that was finished, I remember at the time the researchers said when they finished off mapping the human genome, that was the beginning, not the ending. That was all we had then was the plan of what was actually in the code. We had to learn what it actually meant and what we could do with it. And this is starting to happen. We're entering the age that some people call of post-genomic medicine. Medicine when we can understand ourselves and the way we interact with drugs, where we get diseases at a genetic level. In terms of this technology, we have to be able to sequence people's DNA very rapidly and very cheaply to use this technology. And whilst we have Moore's law that says that the speed of computers keeps increasing and the cost keeps falling over time very rapidly, we have a similar concept, actually come up by an economist, called the Carlson curve, which describes this for genomic sequencing. And you can see that on this slide here. Note the logarithmic scale on the vertical axis, which basically shows that back in 2001, that long after the completion of the Human Genome Project, it was still costing about $100 million to sequence a human genome. It cost about $3 billion when we did the Human Genome Project. And we got that down to about $1,000 genome in, I think it was just earlier, 2014. And today it's below $100 a genome. We can sequence a genome in a matter of hours. It'll fairly soon be a matter of minutes. It'll be less than $10, less than $1. And when you can sequence people's genomes that cheaply, it opens up all sorts of possibilities in medicine. What are the implications of this? Well, for a start, diagnosis should get better because we'll be able to understand what conditions people are likely to have, because they've got a genetic predisposition to have a particular condition, which of course raises massive ethical and business implications. What about insurance? If you could do a genetic test of someone before they apply for insurance and you know they were going to get certain diseases, do you not offer them certain types of cover? All sorts of questions like that come into existence. It also, though, opens up, once we've got the ability to sequence genomes, the opportunity to use what's called pharmacogenomics, which is not where you genetically treat people's health conditions. It is where you actually understand them better through genetic sequencing, and you prescribe conventional drugs based upon genetic understanding of the patient. So if two people get exactly the same disease and you give them both the same drug, the chances are they'll react to that drug differently. Some people might have a great reaction to a drug, might cure them very quickly. Some people cure them slowly. Some people it has no impact at all. Some people might even get an adverse drug reaction. We hope that won't happen because they test drugs significantly. But what I'm saying is different drugs work differently in different people. And the reasons for that are often genetic. And if you can actually work out who will react in a certain way to a certain drug, you can prescribe drugs better. And it also means, from the point of view of businesses, lots of drugs that have been developed have never got to market because they would have been dangerous for certain people. And you didn't know who those people were, therefore you couldn't put the drug on the market. But if you can sequence people's genomes and prescribe based upon their genetic makeup, suddenly lots of back catalogue of drugs become potentially very viable. There's massive economic implications of pharmacogenomics. Think also to what's going on in the world today with coronavirus. We know that some people, when they get it, get very, very ill very, very quickly, and it can be serious, it can be fatal. Most people get it asymptomatically or have very few symptoms. That's probably linked to a large extent to their genetic makeup. So if we had sophisticated pharmacogenomics available today at a low cost, we could actually work out potentially what were the genetic predispositions that mean you're more likely to be more seriously impacted by coronavirus, and we could shield just those people rather than to make decisions based upon a much more blunt instruments as we are today. We would have a very different reaction to the pandemic if we could sequence everybody's genome rapidly and cheaply and use that to decide who was most at risk of complications from COVID-19. Looking further ahead in the world of post-genomic medicine, we will start to see genetic therapies, the ability to change the genetics of our bodies to remove potential problems. This, of course, raises all sorts of concerns about what we see as a medical condition versus someone's individual makeup. Should we seek to remove genetic, if you like, defects, to use a word from people? That's a very, very charged issue, gets you into issues like eugenics, but certainly I don't think the genie will be put back in the bottle. When we have sophisticated artificial intelligence, you put this together with genetic sequencing and the ability to actually re-engineer our DNA using synthetic biology, all sorts of issues arise. Think back to the start of what I was talking about here in this lecture. I was talking about the impossible becoming possible, which is what Singularity is about. This is the biggest one. For years and years and years, we've been limited what we could do with our own biology. That's not going to be the case in the future. Final technology linked to this is bioprinting, slightly more down to earth, but only slightly. I talked about 3D printing back in lecture 3. We looked at all different ways of printing in metals and plastics and things like that, but we can also already print in living tissue. A guy who really started this off was a pediatrician in Japan all the way back in 2002, Makoto Nakamura. And he was basically concerned he saw too many children dying in his unit in the hospital. And he thought, wouldn't it be useful if I could make artificial organs for people who needed transplants or complicated surgery? And so he thought, what if he took human cells, put them into a standard Epson photo printer? He'd worked out that human cells were about the same size as the drops of ink that get sprayed out of a standard photo printer. And he thought, if he sprayed out these cells from a photo printer, he adapted it slightly so he could put layers and layers and layers of cells on top of each other, could he print out, for example, substitutes for human arteries? And when he first tried this, as you might expect, he loaded up his printer, it didn't work, it just clogged up. And he rang up Epson and said, got a problem with your printer. What's that, sir? Well, I've loaded it with human cells, it doesn't work properly anymore. But actually, they'd actually got interested in Epson and they helped him, and eventually he made a working bioprinter that could produce organic tissue using living human cells as the ink, if you like, in the printer. Another pioneer that's taken this forward amazingly is a guy called Gabor Forgax, working now in the United States. And he first printed out back in 2008 cardiac tissue for a chicken. So he made a chicken heart muscle which actually started beating about 70 hours after it was printed out. This was, even the people who work on this find it extraordinary. And he'd spent a lot of his life studying chicken embryos, the way you do and how they develop. And what he basically discovered was chicken embryos, and by inference embryos of all creatures, don't grow the way we thought they did. What they do is they actually grow a load of cells and then they rearrange them. And they grow a load more cells and they rearrange them. So they don't just grow all the right cells in the right places, they just multiply cells up and then put them in the right places. And basically this idea in his head, he thought, well, does that mean if you bioprint things, you don't have to put all the right cells in the right places either. You put roughly the right cells in roughly the right places and they'll rearrange themselves because they're living things. And that actually works. And that's basically how a lot of bioprinting works today. It's an extraordinary concept. Forgax went on to form a company, which is now a public company in the States, Organovo, and it developed its first commercial bioprinter all the way back in 2009. And what this does is to basically get loaded up with an aggregate of cells, so they don't get all of the individual cells that need printing, at all the different types of cells they need, pull them all together in a mix and form them into little spheroids which contain tens of thousands of cells, and they basically place these little spheroids using a needle-based system into what they call biopaper, which is basically water with something to hold the surface tension together more strongly, so a bit of hydrogel, the collagen in there, for example. And then once they've positioned the cells, they rearrange, they self-assemble. And it's worth thinking back to what Rob was talking about in electron synthetic biology and nanotechnology, where again, self-assembly was a big concept going on in certain forms of nanotechnology research. You'll see the same concepts coming back again and again and again in the technologies we've looked at across this module. By November 2014, Organova was actually selling bioprinted human tissue for use in drug testing, not for going into patients, but you could already buy these days human liver tissue or human kidney tissue as commercial products. So they print out, I think it's about 400 samples of liver and kidney tissue Organova every month to be sold on, for example, doing cancer testing. It means you can test a new drug on exactly the same sample again and again and again because it's been printed out by the system. They're also hoping to start doing human trials of things like bioprinted nerve grafts in surgery in the early 2020s. It was last 2021, the last date I saw for this. They have consistently delivered ahead of schedule at Organovo. It is quite possible we'll be printing parts of human beings using an organic 3D printing technology in certainly this decade. I think that's likely to happen. Here's a diagram showing you the process. You can see up here, first of all up here we've got a single layer of bio-ink spheroids just put into the bio paper, the collagen, multiple layers are put there, and then what this diagram is trying to show you is that then the cells rearrange. So the cells that should be on the inside of a blood vessel, for example, move to the inside, the ones that should be on the outside move to the outside, etc. It takes many hours, takes about 70 hours typically for cells to rearrange, and you do have to keep the cells alive whilst they're doing this. But this is basically the process. So it means you don't have to put exactly the right cells in exactly the right places. Even the people who do this are amazed it works, but it does. In terms of where this is taking us, there have been many experiments around the world in this. Very interesting experiment a few years back by a guy called Jeremy Mao and his team in the United States, where they tried printing scaffolds to put into people's mouths. They tried it initially in rats, where it would allow you to regrow a tooth. Basically, many animals are quite good at repair, as we know. If you cut yourself, you mend. But if you have a major injury, the body can't reform something. But if you give it a bit of help with a bioprinted mesh, it possibly can. They tried an experiment in rabbits where they actually broke their hip bones and took out the bone to put a mesh back in, and the rabbit regrew a bone. So the idea of someone actually having a problem with a hip joint and not having a hip implant, but actually growing a new hip is possible within the next 10 or 20 years. We've seen work on in situ bioprinting, which means basically if you've had, say, a burn, removing damaged cells and printing on new cells where you need them on the body to save you having, say, a skin graft. This has been pioneered by the Wake Forest Institute of the United States, backed by the US military. There's also a company run in Russia called Bioprinting Solutions, which has now printed thyroid glands and put them into mice who have lived for many weeks with a completely bioprinted thyroid, while getting rather clever at making things digitally, which before this point in time have only been done by, if you like, by nature itself. You take this to its extreme, you start to think, well, will we end up to a point where we don't just use bioprinting to solve medical problems, to give people transplant organs, things like that? Will we use it to alter ourselves, for example, cosmetically? We know already L'Oreal are working with Organovo, they have been for many years, on 3D printing bioprinted skin, potentially for use in testing of cosmetics, so you don't have to do animal testing. But we might be heading towards a point in time where you get things like this, where we could actually print directly onto the body. So you could get yourself scanned when you were young and have your face reapplied every 10 years to give yourself, perpetual youth. Or if you wanted to have bigger muscles, you wouldn't have to go through all the process of exercising. You could just have new muscles printed into your body. There are all sorts of weird implications here, and it's worth remembering that one of the biggest industries in the world is the industry for health and beauty. Cosmetic surgery didn't exist as an industry really 30 years ago at a level of scale. It's now a massive industry, and people may start to demand these kinds of what to us today seem truly grotesque and magical types of medical services. Now, that gets us towards a question. So we've got a little picture board here, got 4 pictures. First of all, up here we have Nicolae Copernicus, the guy who came up with a theory of a heliocentricity, the idea that the Earth went around the Sun rather than the Sun going around the Earth. We then have Charles Darwin, who came up with a theory of natural selection, that we actually evolved from animals, and I'm sure you're aware of that. And then here we have Sigmund Freud, who came up with the idea that our conscious and our subconscious are sort of linked, and that our subconscious desires and thoughts affect our conscious activity. So the question here, what comes next? And the idea is all of these people, they all challenge what we could call a discontinuity. They challenged the view of the specialness of the human species. Basically, Copernicus said we weren't at the centre of the universe. We were just an insignificant bit of it going around something else. Charles Darwin said human beings were not distinct from the animal kingdom. We were just evolved out of it. We weren't particularly special in the animal kingdom either. And Freud started to say that there wasn't an absolute divide between the conscious and the subconscious, which again is slightly disturbing. So all these people made us question the uniqueness, the position we'd like to put ourselves in of the human race. So what comes next? Well, this was all talked about in a very interesting book by a guy called Bruce Majlis, and he basically said that these people challenged the first three discontinuities, and the fourth discontinuity is the idea there is a conceptual divide, an absolute binary division between human beings and machines, which I think until this point in time we've imagined. We always talk about capital and labour, technology and people as if they are distinct, but that won't necessarily always remain the case. And he says this divide is being broken down, which doesn't mean that people and machines are the same, just simply they're on a spectrum. This divide is being broken down when A, it's no longer reasonable to think of human beings without machines, and secondly, when the same paradigms explain and govern the workings of human beings and artificial mechanisms. And as I hope you're reflecting on at this point, the material I've just been talking about is very much about this. When we start to think about creating artificial intelligence and augmenting our own intelligence, when we start thinking about bioprinting bits of people, changing our own genetic makeup in response to genetic testing, this is about saying that the same digital technologies we use for communication, to run our computers, to run our businesses, are the same technologies and understanding we'll use to change ourselves. That breaks that divide of absolute difference between human beings and technology. This takes us back to the idea we've seen many times across the module of convergence and boundaries falling, particularly with the one that I just mentioned of technology and labour. Before the Industrial Revolution, they were distinct, and then what's been happening over the past, well, ever since, has been the two coming together. And I talked about this in some depth in Lecture 7, where we talked about automation, the implications of artificial intelligence and robots on jobs, because the opportunities to substitute technology and people were getting more and more significant. And really what Majlis was talking about all the way back in 1993, an extraordinary book, was exactly this blurring divide between people and machines. Now, that concept at its most extreme comes into this concept of transhumanism, which is the idea we should take a proactive role in upgrading ourselves. A view that was first talked about by Julian Huxley, actually was the brother, I think, of Aldous Huxley, all the way back in 1927. He gave us this word, transhumanism. This has been a very controversial idea ever since. Probably the most controversial person to write about it was a guy called Max Moore, who defined transhumanism, we can see here, a class of philosophies of life that seek the continuation and acceleration of the evolution of intelligent life beyond its currently human form and human limitations by means of science and technology. There's a lot in that definition. Max Moore's paper on this keeps getting taken down off the internet, put back again. There's a lot in that paper that offends people of a religious point of view. This is very much a reductionist view of the world, because Moore's view is basically we are a form of technology. We just understand the technology and then we can upgrade it. This is the idea, for example, that medics, when we talk about doctors making people better at the moment, they don't. Doctors don't make people better, they return them to the state they were at before they were ill. If doctors made people better, they would enhance them. It's the idea that we expect upgrades in everything around us all the time. When you get a new smartphone, you expect to have more features than the previous smartphone. When you have a child, you don't expect your child to have more functionality than you have. And yet, in a transhuman world, a world where we consciously trying to upgrade ourselves, you'd expect that to be happening. This is a very contentious point of view, but it feeds directly from the sort of stuff we've been talking about. Transhumanism is also something that is rising up, and it's important to recognise this is not a technology, this is a philosophical or political viewpoint. There is an organisation called Humanity Plus that actually maintains a transhumanist declaration. You can find it online if you want to look more deeply into this. And we've started to see real world politics being influenced by transhumanism. There's a paper by Benedicta and Seidman from 2016 that you've got on the reading list. If you want to read one thing from this lecture, read this paper, because it really is quite startling when you realise there are now political parties around the world you can vote for in elections who are proposing we should be advocating transhumanism. This is still minority politics. Not many people think we should be upgrading ourselves using technology, bioprinting, genetics, cybernetics, etc. But I think if you look at where it sits, probably it's advanced today as a political movement as the Green Movement was several decades back. And of course, the Green Movement's become part of mainstream politics today. We do not know where it will go. Is it going to be the case that most major political parties slowly get on board with this? When the opportunities to change ourselves and technology get so great, people will actually wish to have them. Now, many people today would say, well, who would want to be upgraded? Who'd want to have a chip in your head to make you more intelligent or connected to people or whatever it was? That's bonkers. But then people 20 years ago, if you'd said to them, do you want to have a device which gives you communication and access to this thing called the internet, you keep with you all the time so you constantly can be online and linked to people, they would have thought that was horrific. And yet most people today think smartphones are a good idea, apparently. And so over time, we see attitudes to technology and its integration into our lives and our culture and potentially our bodies changing. It's a very interesting thing. Where are we going to go with technology in the next sort of 10, 20, 30 years? What will become possible, not just technologically, but conceptually, politically, socially? And of course, the implications are enormous. We'll finish off just looking more broadly at all this. Singularity is about making the impossible possible. And one of the themes that's going to cross this module is that digital transformation is made possible by digital technology, but there has to be a reason to want to engage in that transformation in the first place. And whilst at the moment the world is obviously focused on the pandemic and how we deal with that, and that might involve all kinds of technology in the end, the bigger issue we face as a species is resource availability. And what you see on this slide is basically a plot from the United Nations Environment Panel back in 2010, showing us all the stuff used by the human species in a year, which was about 50 billion tonnes of stuff back in 2010. And they reckon if nothing changed by 2050, about 140 billion tonnes of stuff a year. We use almost 3 times more stuff by 2050. And you'd have to be a resource scientist to recognise that stuff will not exist, or it won't exist for very long, or using that stuff would have such horrific consequences, not least for climate and pollution, we shouldn't use it anyway. So the big issue we face is how do we deal with resource availability on a planet with increasing demands for stuff, not least because of more and more people. And one of the arguments around the singularity is if the impossible becomes possible, if we learn to control organic matter, to make organic technology, to make, for example, devices that can take carbon out of the atmosphere so we can deal with climate change, all these things might become possible due to singularity developments. There is very much a point of view in futurist circles that says we should pursue the singularity, we should pursue the most advanced technology we can because it's this technology which will solve our problems, rather than saying we should learn to live within our means, use less stuff, create less pollution, etc. It's also the case, of course, that maybe we won't be able to deal with it anyway. Whatever we do with technology, you can't deal with the fact there's a finite amount of stuff on planet Earth. And there's a whole other set of arguments here, which I haven't got time to go into in this video, which are basically about saying the only way we can survive long term as a species is to actually find more stuff. Yes, we'll probably have to consume less a bit, but we need to find more. We go beyond the Earth. What you see here is a graphic from a company which was called Deep Space Industries, which was set up to do asteroid mining. real company. Another one called Planetary Resources was also set up a few years ago. Neither are now trading it in that form, unfortunately. But the idea we will have to leave this planet, maybe changing our bodies in the process, to find more stuff, at least some of us, to keep our civilization going, that's a whole other area associated with the singularity. If you're interested in this, I've got a set of videos called The Resources from Space, which is what you'll find on my Explaining the Future YouTube channel. So, we'll finish off with a few thoughts. Singularity or decline. Linking back to what I've just talked about. Do we need to get to a point of singularity to survive? That is a perfectly reasonable question. Some people today are of the view that we can basically ignore all the problems of the world because if technology gets good enough, we'll be able to deal with those problems. And that's, of course, an excuse to do nothing about things like climate change, but it actually might be, in the longer term, the best solution. Human beings are not very good at going backwards. Or are we going to see a backlash against all this technology? You might have listened to this lecture and watched this lecture and gone, this is horrific. We don't want bioprinting and genetic modification and cybernetics. We should stop and pull back. We're seeing some thoughts about that at the moment during the pandemic. Maybe we'll be using a lot less digital technology in the future, although as the pandemic has shown us, we are now linked together digitally more successfully and importantly than ever before. I think this backlash is less likely now than it was 3 or 4 months ago. What does look fairly certain is that digital transformation looks set to change the nature and context of work, of ourselves and our society in the years and decades ahead. As I said, and I think Rob said as well back in lecture 1, and since then, this term digital transformation is daft. It's just another piece of spin from the business consultants about what's going on. But the things behind it, the technology we've looked at across this module, what I had in that table at the start of this lecture, those technologies are very real, with very real implications. They're linked together. And as we move towards developing all of these, the way they interact, it might take us towards this point of the impossible becoming possible, another singularity. And what I hope I've stressed in this lecture more than anything else is that all this change is not just about a new wave of automation. It's not just about robots and AI and a bit of cloud computing and big data analysis. It's about something far more fundamental. We've already started mixing in to digital technology, synthetic biology, genetic medicine, molecular self-assembly. These things change our relationship with and understanding of and control of the physical world. And you add in quantum computing, which changes our understanding of quantum systems, which basically means all the matter around us everywhere. And what we could do with technology explodes beyond possibility. Maybe that's the best way to put it. And that really is what the singularity is all about. So that is the end of this lecture. Hopefully it's given you some things to ponder on, to think about. I would encourage you to watch my videos on quantum computing and brain-computer interfaces and cyborg fusion, which very much link into this. And I hope you all do well in your project and in the remainder of your academic career and beyond.